67th. In an earlier section, we obtained the general equation for the potential. Potential equals sum of charges divided by the square root of the sum of the squares of the differences in coordinates. If r denotes the distance of the point x, y, z from the origin, and r sub I the distance of the charge E sub I at coordinates x sub I, y sub I, z sub I from the origin, we may write this in the form potential equals sum of charges divided by the square root of r squared minus 2 times the sum of the products of the coordinates of x, y, and z with their respective charge positions x sub I, y sub I, z sub I, plus r sub I squared. At a great distance from the origin, this may be expanded in descending powers of the distance in the form potential equals sum of charges divided by r plus sum of charge times its respective coordinate positions divided by r squared, plus 1/2 of sum of charge times the square of its respective coordinate positions divided by r cubed, and so on. The term of order 1 divided by r is simply the total charge divided by r. The term of order 1 divided by r squared is the sum of the charge times its respective coordinate positions multiplied by the corresponding coordinate components x, y, and z. If the origin is taken at the centroid of the charges at x sub I, y sub I, z sub I, so that the summation of charge times x sub I, charge times y sub I, and charge times z sub I are all 0, then by choosing the centroid as the origin, the term of order 1 divided by r squared disappears. The term of order 1 divided by r cubed is given by the sum of charge times r sub I squared minus 1/3 of the moment of inertia about the line joining the origin to the point x, y, z. Let A, B, and C the moments of inertia about the coordinate axes of the charge E sub I at x sub I, y sub I, z sub I, and let I be the moment of inertia about the line joining the origin to the point x, y, z. Then we obtain sum of charge times r sub I squared equals sum of moments of inertia A, B, and C. Sum of charge times the square of the coordinate positions equals sum of charge times r sub I squared minus the moment of inertia I. Thus, taking the centroid of the charges as the origin, the potential at a great distance from the origin can be expanded in the form potential equals total charge divided by r plus 1/2 of sum of charge times r sub I squared minus 1/3 of the moment of inertia divided by r cubed. Thus, except when the total charge sum of E vanishes, the field at infinity is the same as if the total charge sum of E were collected at the centroid of the charges. Therefore, the equipotentials approximate to spheres having this point as their center, and the asymptotes to the lines of force are radii drawn through the centroid. These results are illustrated in the special fields of force considered in earlier sections. 68th. The lines of force from collinear charges. When the field is produced solely by charges all in the same straight line, the equipotentials are obviously surfaces of revolution about this line, while the lines of force lie entirely in planes through this line. In this important case, the equation of the lines of force admits of direct integration. Let positions p sub 1, p sub 2, p sub 3, and so on be the locations of the charges e sub 1, e sub 2, e sub 3, and so on. Let q and q prime be any two adjacent points on a line of force. Let n be the foot of the perpendicular from q to the axis joining the charges, and let a circle be drawn perpendicular to this axis with center n and radius qn. This circle subtends at the charge p sub I a solid angle given by 2 pi multiplied by 1 minus cosine of the angle qp sub I n. Thus, the surface integral of the normal force arising from charge E sub I taken over the circle Qn is given by 2 pi E sub I multiplied by 1 minus cosine of the angle Qp sub In. The total surface integral of the normal force taken over this surface is given by the summation of 2 pi E sub I multiplied by 1 minus cosine of the angle Qp sub In. If we draw a similar circle through Q prime, we obtain a closed surface bounded by these two circles and by the surface formed by the revolution of the segment QQ prime. This surface contains no electric charge, so that the surface integral of the normal force taken over it must be 0. Hence, the integral of the force over the circle Qn must be the same as that over the similar circle drawn through Q prime. This gives the equation of the lines of force in the form summation of charge times cosine of the angle is equal to a constant. Analytically, let the point P sub I have coordinates x sub I 0, 0. Let Q have coordinates x, y, z. Then, cosine of the angle is given by the difference x minus x sub I divided by the square root of the sum of the squares of x minus x sub I, y, and z. The equation of the surfaces formed by the revolution of the lines of force is then given by summation of charge times the difference x minus x sub I divided by the square root of the sum of the squares of x minus x sub I, y, and z equals a constant. It will easily be verified by differentiation that this is an integral of the differential equation for the electric field lines. 69th. We have seen that in general, the equipotential through any point of equilibrium must intersect itself at the point of equilibrium. Let x, y, and z be a point of equilibrium, and let the potential at this point be denoted by v sub 0. Let the potential at an adjacent point x plus xi, y plus eta, z plus zeta be denoted by v at this location. By Taylor's theorem, if f of x, y, z is any function of x, y, and z is any function of x, y, and z, we have the expansion function at displaced point equals function at original point plus the first order partial derivatives multiplied by the displacements plus 1/2 of the sum of the second order partial derivatives multiplied by the squares of the displacements plus higher order terms. Taking the function f of x, y, and z to be the potential at x, y, and z, this of course being a function of the variables x, y, and z, the foregoing equation becomes potential at the displaced point equals potential at the original point plus first derivatives of the potential with respect to x, y, and z multiplied by the respective displacements plus 1/2 the sum of the second derivatives multiplied by the squares of the displacements plus higher order terms. If x, y, z is a point of equilibrium, then the first derivatives of the potential vanish, so that the equation simplifies to potential at the displaced point equals potential at the equilibrium point plus 1/2 the sum of the second derivatives multiplied by the squares of the displacements. Referred to x, y, z as origin, the coordinates of the displaced point x plus xi, y plus eta, z plus zeta become xi, eta, zeta, and the equation of the equipotential at the displaced location becomes sum of second derivatives of the potential multiplied by the squares of the displacements equals constant. In the neighborhood of the point of equilibrium, the values of psi, eta, and zeta are small, so that in general the terms containing powers higher than squares may be neglected, and the equation of the equipotential simplifies to a quadratic form. In particular, the equipotential passing through the equilibrium point becomes identical in the neighborhood of the point of equilibrium with the cone, sum of squared terms weighted by second derivatives equals 0. Let this cone, referred to its principal axes, become a times I squared plus b times eta squared plus c times zeta squared equals 0. Then, since the sum of the coefficients of the squares of the variables is an invariant, a plus b plus c equals 0 is the condition that the cone shall have 3 perpendicular generators. Hence, we see that at the point at which an equipotential cuts itself, we can always find 3 perpendicular tangents to the equipotential. Moreover, we can find these perpendicular tangents in an infinite number of ways. In the particular case in which the cone is one of revolution, such as when the whole field is symmetrical about an axis, as in earlier figures, the equation of the cone must become xi squared plus eta squared minus 2 zeta squared equals 0, where the axis of zeta is the axis of symmetry. The section of the equipotential made by any plane through the axis, say that of eta zeta, must now become a hyperbola in the neighborhood of the point of equilibrium. This shows that the tangents to the equipotentials each make a constant angle of 54 degrees 44 minutes with the axis of symmetry. In the more general cases in which there is no symmetry about an axis, the two branches of the surface will, in general, intersect in a line, and the cone reduces to two planes, the equation being a times xi squared plus b times eta squared equals 0, where the axis of zeta is the line of intersection. We now have a plus b equals 0, so that the tangent planes to the equipotential intersect at right angles. An analogous theorem can be proved when n sheets of an equipotential intersect at a point. The theorem states that the n sheets make equal angles pi divided by n with one another. This is known as Rankin's theorem and can be found in Maxwell's Electricity and Magnetism, section 115, or Thomson and Tate's Natural Philosophy, section 780. 70th. A conductor is always an equipotential, and it can be constructed so as to cut itself at any angle we please. It will be seen that the foregoing theorems can fail either through the coefficients a, b, and c all vanishing, or through their all becoming infinite. In the former case, the potential near a point at which the conductor cuts itself is of the form second derivatives of potential multiplied by squares of displacements, so that the components of intensity are of the forms third derivatives of potential multiplied by cubes of displacements. The intensity near the point of equilibrium is therefore a small quantity of the second order, and since by Coulomb's law the electric field intensity is proportional to 4 pi times the surface charge density, it follows that the surface charge density is 0 along the line of intersection and is proportional to the square of the distance from the line of intersection at adjacent points. If, however, the coefficients a, b, and c are all infinite, we have the electric intensity also infinite, and therefore the surface charge density is infinite along the line of intersection. It is clear that the surface charge density will vanish when the conducting surface cuts itself in such a way that the angle less than 2 right angles is external to the conductor, and that the surface charge density will become infinite when the angle greater than 2 right angles is external to the conductor. This becomes obvious on examining the arrangement of the lines of force in the neighborhood of the angle. 71st. The arrangement shown in the corresponding figure is such as will be found at the point of a lightning conductor. The object of the lightning conductor is to ensure that the intensity shall be greater at its point than on any part of the buildings it is designed to protect. The discharge will therefore take place from the point of the lightning conductor sooner than from any part of the building, and by putting the conductor in good electrical communication with the earth, it is possible to ensure that no harm shall be done to the main buildings by the electrical discharge. An application of the same principle will explain the danger to a human being or animal of standing in the open air in the presence of a thundercloud, or of standing under an isolated tree. The upward point, whether the head of a man or an animal, or the summit of the tree, tends to collect the lines of force which pass from the cloud to the ground, so that a discharge of electricity will take place from the head or tree, rather than from the ground. 72nd. The property of lines of force clustering together in this way is utilized also in the manufacture of electrical instruments. A cage of wire is placed around the instrument, and almost all the lines of force from any charges which there may be outside the instrument will cluster together on the convex surfaces of the wire. Very few lines of force escape through this cage, so that the instrument inside the cage is hardly affected at all by any electric phenomena which may take place outside it. The cording figure shows the way in which lines of force are absorbed by a wire grating. It is drawn to represent the lines of force of a uniform field meeting a plane grating placed at right angles to the field of force.